A partial plan is a solution for a given planning problem if it contains no more flaws. So our goal test will be to check whether our partial plan is a flawless partial plan. Of course, we haven't defined a flaw yet, so that's what we will do next. And when we have done this, the search problem will be complete. We have defined the initial state, we have defined the successor function, and we will now look at the goal test. I will now introduce the concept of a threat in a partial plan, and I will use an example to illustrate this. What we see here is a partial plan to which I've already added two actions to support the two goal conditions. We also see the dummy action for the goal over here, and there should be a second dummy action for the initial state, but since we're not going to use that in this example, I've left it out here to save a little space. Now what we do is apply more plan refinement operations. In this case, we add an action to the plan, this new move action over here. And the reason why we do this is because we want to support the precondition at robot location 1 with this new operator. So we have inserted a causal link for this, and we also insert an ordering constraint because the action that is the provider must come before the consumer. Now let us also have a look at the conditions that are protected by the causal links. These are at robot location 2 here, then not unloaded robot here, the two goal conditions that we want to support, and over here it is the precondition of the load operator that the robot must be at location 1 that we're protecting with this causal link. Now the problem is the following. Our first operator, the move action, has a negative effect at robot location 1, which is exactly the condition we're trying to protect down here. This means if we first executed action number 3, the move robot location 2 location 1, then action number 1, moving the robot from location 1 to location 2, and finally action number 2, loading the container onto the robot with the crane, etc., then this plan would not be valid because the second action in our totally ordered plan would destroy the protected condition that we need to execute the final action in that plan. So the final action would no longer be executable. This is what is called a threat. We have an action that may possibly occur in parallel with a causal link, and that has an effect that is complementary to the condition we're trying to protect in the causal link. That is what is called a threat. And in this case, there's a simple way to get rid of this threat, namely to introduce an additional ordering constraint that says action number 1 must come after action number 2, in which case the action with the effect that is potentially harmful cannot be in parallel to the causal link that protects this condition. So the insertion of the ordering constraint removes the threat, and that is what is called a resolver for this threat. Now that you've seen an example of a threat, here is the formal definition of what constitutes a threat. We start off with a plan pi consisting of the 4 usual components. We have actions, orderings, variable bindings, and causal links. In this plan, we have an action AK that may cause a threat for a causal link that links an action AI to an action AJ, protecting condition P. And we say that the action AK threatens our causal link if the following 3 conditions hold. Firstly, AK must have an effect, not Q, that is possibly inconsistent with P, the condition we're trying to protect. If P and Q are ground, then of course they are possibly inconsistent if they are the same. But if they contain variables, then they are possibly inconsistent if P and Q are unifiable. That means they can be made the same if we substitute values for variables. The second condition is that the following ordering constraints must be consistent with the ordering constraints in our plan. And the ordering constraints that we consider are AI could come before AK and AK before AJ. What this means is that our action AK can possibly be in parallel to the causal link because the provider comes before AK and the consumer comes after AK. But the condition here is that this is possible, not that it's necessarily so. So these orderings constraints must be consistent with our orderings in the plan, but they need not be in the plan. Similarly, the third condition states that if we introduce new variable bindings as part of our unification up here, then these new variable binding constraints must be consistent with the binding constraints that we currently have in our plan. So, AK can threaten our causal link if it has an effect that is possibly inconsistent with the proposition we're trying to protect, and it may possibly occur in parallel to our causal link. And finally, the bindings that we need for making P and Q the same are consistent with the bindings used in the plan. That is the definition of a threat. Threats, however, are not the only types of flaws that can occur in a plan. The good news is there are only two types of flaws we need to look out for. So in a plan pi that consists of the usual four components, we can have two types of flaw. The first is an unsatisfied sub-goal in that plan. And an unsatisfied sub-goal is a precondition of an action that does not have an incoming causal link that supports it. So this could be the goal dummy action, which of course has all the goal conditions as preconditions. All of those need to be supported for the plan not to have this type of flaw. And then every action that we have added to the plan also must have all of its preconditions supported by a causal link for the plan not to have this type of flaw. And the second type of flaw is a threat. So that's what we've just seen, an action that may interfere with a causal link. And that's it. That's all the types of flaws we need to consider. And here is the proposition that gives us our goal test. Suppose we are given a partial plan consisting of actions, orderings, bindings, and links, and we can say that this is a solution to a planning problem consisting of a state transition system, initial state, and goal if three conditions hold. The first one is that the plan pi has no flaw. That's the two types of flaws we've just described. Then the ordering constraints must not be circular, so they must be consistent, and the variable binding constraints must also be consistent. So while we are doing our search for a plan, we have these three conditions to maintain. The first one, that a plan must have no flaws, well, we cannot really have that because initially our plan has flaws. The goal has unsatisfied preconditions. But the other two conditions, that we keep our ordering constraints and our variable binding constraints consistent, these two conditions, we maintain this consistency during the planning process. Why is that? Because once we introduce an inconsistency into either set of constraints, this can never be removed. So we maintain the consistency of the constraints and try to remove the flaws from the plan. And once all the flaws are gone, we're done. I won't go into the proof of this proposition in detail, but just tell you that this can be done by induction quite easily. So we start off with the base case, that is the empty plan. And in the empty plan, the only causal links can go from the init action to the goal action, the two dummy actions that we have in this plan. And if all the goal conditions are supported from the initial state, that must be a solution plan to our problem, in which case the goal was already satisfied in the initial state. And the induction step simply consists of removing one action from the plan and showing that this shorter plan now still is a solution to a planning problem, a modified planning problem. And the action we pick here, as you can see, is one of the actions in the plan that has no predecessors. So, this is it. This is our goal test that completes the planning problem. And our goal test is that our plan must not have flaws. If it has no flaws, it is a solution plan.